and welcome everybody to, let's see, what day is it? It's Saturday. It's Subnet Saturday. So great to have you. I've been doing a few tweaks in my office, and I am so glad you're here. Our focus today is pretty straightforward. What we're going to do is we are going to focus on being able to convert from a decimal number like 50 or 87 or whatever that number is into binary. Now, this skill isn't just good for, at a party, as a party trick. This is going to become an essential skill in our tool belt. So what we've been doing so far in this playlist for Subnet Saturdays is we are putting these individual components in our tool belt. First of all, understanding what binary, so you can say you do them. They are very useful as we get into the subnetting, and we'll be pulling out these tools out of a utility belt like Batman. All right, so our objectives are pretty simple. Let me put up a screen, and let's take a look and try to figure out what the IP address is behind a name. The network service being used would be DNS, the domain name system. Or if the client's trying to access a web server, the application layer service in the background would be HTTP or HTTPS. So the cool thing is the computer does that for us, but as network technicians and engineers, we need to understand how that works. And then that gets pushed down, and then we have some information that's added at the transport layer, and that would be either TCP or UDP, depending on the protocol that's being used. DNS actually uses UDP. And then as that goes down to the layer 3, that's where the IP addressing happens. Layer 3 IP addressing, logical IP addressing. And as you already know from our previous sessions, an IP address is a lot like a street name and a house number. That's really it. So street name, house number. Because you've been part of this channel and part of this Subnet Saturdays, you know that with this IP address, we really don't know where the dividing line is between the network address, which is like a street name, and the house number, which is like a host IP address in IP, until we know what the mask is. And so the mask is the dividing line between those two. So that's old hat. It simply means that the client is sitting on street 10.16.0. We call that the network ID. And the host address is .10, this part over here. And that's because the mask is the dividing line between the two. So now we're all caught up. Now, if you're brand new to this stream, gosh golly, glad you're here. Hope to see you in all the future streams regarding CCNA 200-301, getting us ready with the skills. So my focus in these all these CCNA sessions are to help get you ready with the technical aspects so that when you walk in to either an interview or you walk into the production network, that you have the skills. Like, yeah, I get it. I know what this does. I know how to make it work. And that's my objective, is to give you those skills. So in doing that, I would like to propose at layer 3, let's go ahead and take a look at the screen again. I'd like to propose that, in fact, let's do, at the network layer right here, let's imagine this PC's address. Let me put black up here. Let's imagine this PC's address is 80, let's see here. I've got some notes I'm just peeking at real quick. I made like 5 plans for today, and I'm only going to use one of them, the one I think that'll be the most effective. Okay, let's use 867530.9. So that is the IP address for this client right there. So my question for you with this IP address is, which part of this IP address is the actual network address and which part is the actual host address? That's my question for you regarding that address. What do you think? And if you're saying, Keith, I don't know, unless you tell us what the mask is. The mask is the identifier line. So if I said, and let's go ahead and do this, let's say the mask was 255.255.255.0, which also can be represented as /24 because it means the first 24 bits of the mask are on and the last 8 bits are off. So there's the dividing line right there. That would mean this mask means the network is 86.75.30 and the host address is .9. So this is like the network and this is the actual host. Great. What if we did this? Same IP address, 86.75.30.9, and we used a 16-bit mask, which is 255, first octet, second octet. That's a 5. It's going to be a 5. I'm going to make it a 5.0.0, and that can be represented as the first 16 bits from left to right in the mask. And then the dividing line is here. So it's pretty easy to look at the mask and look at the dividing line. But here's the challenge. What if, and this is going to apply directly to our converting between binary and decimal, what if we had a mask like this one right here? What if we had a mask of /, and let me look at my notes so I can stay on track. yeah, let's do this. Let's say we had a mask of /18. So that's our mask. Now, we have a new challenge here because this mask of 18 isn't on a clean boundary of an octet. And so let me share with you here. If somebody said, yeah, the mask is 18, the IP address is 86.75.30.9, and the mask is 18, if we had to plug in that IP address, and let me go ahead and clear all of this. If we had to plug in that IP address to a computer, and we had to do 86.75.30.9 with an 18-bit mask, what would that look like as a mask? Because I know the first number in the mask would be 255, no problem there, because that's 8 bits, so that's 8 bits. And then the second octet in the mask would be another 8 bits. That's 8 more, and that would take us to 16. But how do we represent 2 bits in this third octet here? So I'm going to put a little box there, meaning we're not, and that little box simply means we don't know yet what that's going to be. And then the last number for the mask is going to be A0. So we need to find out what the decimal number is going to be there to represent that we need 2 more bits, and then the rest of them are going to be off, just like that. So I'd like to share with you how we could solve that problem, and here's the answer. We take that third octet. Oh, by the way, if you hear that noise in the background, I have a faucet, a shower head that's faucet that's just pouring water out of it. So a plumber came earlier today, and I was getting ready for the live stream, and I usually shower before a live stream. I want to look good for you, so I couldn't shower because the water's off. And I went to brush my teeth, went to rinse. No water. So fortunately, I had a few bottles of water lying around. Anyway, so if you hear some noise in the background, that's him. His name is Jose. He's a great guy. Anyway, he's getting me solved. So the challenge here is if we had to put this IP address in to a computer or a router interface or a computer, what would we use for the mask to indicate that we're going to use the first 8 bits of this octet for the network, this 8 bits for this octet, and only 2 bits of this one? And the answer is to go ahead and do what I almost do on every single exam that involves networking, and that is write out the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. So if you ever find yourself in a situation with IP addressing where you don't have a calculator handy, maybe it's a test environment, maybe you're just doing some practice, that if you're not sure what to do, write out that table, the powers of 2. Starting on the far right with a 1, then double it 2, 4, 8, 16, 32, 64, 128. That'll get your brain going at least with that table in place. And then here's how we could use this to figure out the mask. If we expand this to have this represent those 8 bits there, we know that the first 2 are 8 plus 8 is 16. So let's imagine that this is the boundary between the second and third octet. So the second octet goes that way, and the third octet is going this way, this third number that we're dealing with. So if we need 18 bits, we already have 16 in place, and we would just add the additional bits. So 16 plus 17 plus 18, and stop. I usually draw a little dividing line there, and then the rest of these would be 0. So that's what the mask would look like in that third octet if we had a /18. 8 here, full 8 here, plus 2 there would look like this. Now, the question is, and if you were present in our last live stream, and it's all in the playlist as well, you can answer this question about how to put it into the computer now, because we have to put it in decimal. So you can't put it in binary. We can't just put in 11000000. It won't take it. So we have to actually figure out what that is in decimal so we can put it in the computer. So the way we could solve that is the way we did in our last session, and that is you take these 8 bits and you add up the bits that are on. And that would be 128, because that bit's on, plus 64, because that bit's on, plus 0. There's nothing left there. So 128 plus 64 is a whopping 192. So our mask right here, and I'll put some nice bright color for us, will be 192. So if we went to a computer and said, hey, Mr. Computer, your IP address on this interface is 86.75.30.9, and there's an 18-bit mask, we would implement that by doing 255, that's 16 bits of the mask, plus 192, which represents that the first 2 bits of that third octet are being used for the network and nothing after that. And again, the good news is with subnet masks is they have to be contiguous. It has to go 1, 1, 1, 1, 1, 1, 1, stop, all zeros after that. No picking and choosing about where we're going to start and stop. Masks are always contiguous. So it's going to be all bits on until they're not. And that's the dividing line, just like this right here. And that's the dividing line between network portion and host portion. Where the bits stop, that identifies the dividing between the network and the hosts. So what I thought we could do is let's actually implement this with the 18-bit mask. So in theory, if it works correctly, it should go something like this. Let me go ahead and hide all that for just a moment. And let's go to a router interface and let's configure it. And let me log in. That actually makes it even better. Okay, so let's pick R6 in this topology, and let me do a show IP interface brief. And I'm just going to use another loopback address because they're free, and I can just configure the IP addresses on them. So we'll go to configuration mode, interface loopback, and we'll call this loopback 30, and we'll give it the IP address. 86753099, 86753099. And if you're wondering why I chose that address, Tommy Two-Tone from the 80s. Anyway, little inside chuckle there. All right, so that's the address, and now we need to put on an 18-bit mask. So the 18-bit mask, as we just calculated, looks like 255, that's 8 bits, the first 8 bits, and then 255, the second set of 8 bits, and then a 192, which means the first 2 bits of that third octet, .0, and that's our mask. Ta-da! Now, to verify that, check this out. We can do a show IP interface for loopback 30, and that's going to show us a lot of detail regarding that interface, but most importantly, I just wanted to show you that here is the IP address and the mask in the slash notation. So when we put a 192 in that third octet, that means those high order 2 bits from that third octet are on the mask. That's why it's a /18. So let's do one more. And here's what I'd like to do. Let me go ahead and clear the screen. And we can actually do the math right here because we've got room. So let's go ahead and do the same IP address, except this time let's use a /19. There we go. So our goal is to use a /19 with the same IP address of 86753099. All right, so a 19-bit mask. How do we represent that? And the answer is, well, Keith, if we're not sure what to do, we're going to write out this table. And then we know that, with a 19, that means we have a 255 for the first number in the mask. That means 8 bits in the mask on. And then the second octet would be another 8 bits. We're making good progress there. And then we need 3 more, so 16, 17, 19. So we take that third number, which is a mystery number at the moment, and we visually represent that. So if we have 16 so far, so here's the 16 boundary right here. So we have 16, this is the second octet going left and the third octet going right. And we're at the 16 boundary mark. If we need 19, it's 16, that's to be 17, 18, 19. I'm just going to draw a line there to visually represent that, and the rest would be zeros. And then the decimal equivalent of that would be add the values that are on up. So it'd be 128 plus 64 plus 32 plus 00000. And that is, we can do this longhand, 128 plus 64 plus 32. So 8 plus 2 is 10, plus 4 more is 14. Great. We have 6, 7, 8, 9, 10, 11, 12. Carry the 1, 224. So this mask would be 224 in that third octet, meaning that the first 8 bits of the IP address are network, the next 8 bits in the second octet are the network, and in this third octet, these 3 bits are all on, and that's representing the dividing line between network on the left and host on the right. And the way we would implement that with the mask is 255, 255, 224, which means these 3 bits, .0. Now, to prove that, and to verify that, actually, we could do this. We could go back to our interface, which we're at. I'll just go to interface loopback 30 to make sure I'm on the same interface. And let's put in the IP address again, except this time, instead of 192, let's go ahead and put in the IP address of 224. which represents those 3 high order bits in that third octet, .0, press enter, and then we'll do a show IP interface for loopback 30, and check it out. It's showing us that based on that mask we put in, which is right here by the way, that it is a 19-bit mask. That means 19 contiguous bits from the left all the way to the right, representing a 19-bit network. Okay, so that was a little sneaky way of doing quite a bit of review on binary to decimal, which is all that was from our previous session. That's binary to decimal over and over again. So identifying how many bits we needed, converting that to decimal so we could put it into the computer. Great. So now on to our discussion today, which is decimal to binary. This is a fun game, a lot of fun. And we can use the same screen right here to do that work. And if we want to convert from a decimal number to binary, there's basically 3 steps we can follow, and it works every time. And there is some value in doing this. So it's not just a meaningless exercise. It's actually going to be valuable. Here's what we could do. Whenever we want to convert from decimal to binary, number 1, the first step is to write down the decimal number. So far so good. So let's imagine we want to convert a number like let's pick one of these. Let's pick 75. Let's imagine we want to pick let's do 75. Let's imagine we want to pick convert 75 into its binary equivalent behind the scenes. What is the binary number? So we'd write it down. So 75. Task 1 complete. We've written down the number. Okay, the second step is to go ahead and write out the powers of 2 for the binary. 1, 2, 4, 8, 16, 32, 64, 128. All right, so that's step 2, is to write out the binary values. 128 on the left, all the way to 1 on the right. So you start on the right. That's easier that way. And just start with 1 and keep doubling it until you hit 128. There should be 8 positions there representing each of the 8 bits and a byte. And then we're going to play a game, the game called Does This Go In? It's a great game. Just the first step, write out the decimal number. Second step, write out those powers of 2. And then the third step is play the game called Does This Go In? And I'm going to demonstrate this a couple times, and then I'm going to have you practice it along with me. All right, here's how the game called Does This Go In? Here's how it works. We take the first number here on the left, and I'm going to write down just left. Start on the left. And on the left, we're going to play the game, does 128, I'll put this in a different color, does 128 go into the number 75? I mean, can we divide 75 by 128? How many times as a whole does 128 go into 75? And the answer is, it doesn't fit. 128 doesn't go into 75, not even once. And so we say, oh, bummer. So here's the sad face in binary. Here's the happy face in binary. Yes. So 1's a yes, 0's a no. 1's a yes, 0's a no. So continuing on, what we'll do is we'll say, well, 128 doesn't go into 75. Sad. So we'll put a little sad face there. Aw. All right. Then we keep moving right. 64. Does it go into 75? Yay! It does. So we put a 1 there saying yes, 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 it goes in. And then we do some math. You take that number, 75, and you subtract the 64 because it goes into it, and we're going to find the remainder. So 75 minus, oh, this is going to be easy. I just realized, super easy. So 75 minus 64, there's a 1 there and a 1 there. Great, that's the remainder. And then you go to the next number and you play the same game. Does 32 go into that remainder? The answer is not cleanly, not a whole time. So, sad. Bummer. 0 means no. Think about, sad, sad, sad. And then you go to the next number, 16. Does it go into 11? And the answer is no, it doesn't. It doesn't fit. Not quite. And then we go to 8. Does it go into 11? Yay! Big happy 1. And then we subtract that. It's like accounting. You can only spend the money one time. So you have to account for every time you are going to use a number. So 8 minus 11 minus 8 would be 3 if my calculations are correct there. I think they are. And then we'd go ahead and take that remainder and say, okay, does it go into 3? And unfortunately, no. Bummer. And does 2 go into 3? Yay! So it does. We put a 1 there, and then we subtract 2 from that. And then we have 1 left. And then the question, does 1 go into 1? And the answer is, yes, it does. We put a 1 there, and then we minus 1. And if we have good accounting, it's always going to come out to 0 at the very end. That means every bit has been accounted for. So if we wanted to convert this number 75 into an IP address, into binary, I'm just looking at my notes here to make sure I'm not going to lie to anybody. I'm going to check my math here. So 75, I'll show you my paper. So this is a lot of my scratch from earlier today when I was like writing these out, making sure I wasn't going to have to do something drastic on screen. So for 75, we have 0, 1, 0, 0, 1, 0, 1, 1. Perfect. Awesome. So if we wanted to convert decimal into binary, we just did. This is the binary equivalent. 0, 1, 0, 0, 1, 0, 1, 1 is the binary equivalent of decimal 75. Let's do one more, and we're going to use the same 3 steps. So let's go ahead and clear that off, and let's play the game with the number of 240. So that's our decimal number, and we have 3 steps. 1, write it out. Boom, a third done. 2, write out the table, the binary values. 1, 2, 4, 8, 16, 32, 64, 128. All right, there they are. And then we're going to play the game, does it go in? And so I'm going to say to myself, starting on the left, does 128 go into 240? Last time I checked, it does, cleanly. So we put a 1 there for yes, 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 and then we start doing our math. So 240 minus 128. Okay, so I'm going to carry the 1 there, or bring over the 1, and it's called borrowing, I believe, from my grade school. So there's 2 there, there'd be a 1 there, and a 1 there. Assuming that math is correct, we then play the game with 64. Does 64 go into 112? It does. So we put a 1 there, yay, and then we subtract 64. All right, so I'm going to borrow that, 8, 9, 10, 11, 12, 8, that's great, and then I have to borrow that, that'd be 4. So the remainder is 48. And that's why I do this longhand for you, because you can always get it right if you just take the time to do the longhand. Now, in a production environment, it's very likely that we're going to use some calculators for this. But for certification or for calculations where we're doing custom subnetting or what have you, this is handy to be able to do to verify your work. Because if I was writing an exam, I would write some tricky IP addresses that look like they're in the same subnet, but are not. And so by understanding how to break it apart like this, it's a very valuable skill. I'll also cover that here in just a moment as well. All right. So where were we? Okay, so 64 goes in, yes. Does 32 go into 48? It does. Subtract 32. The remainder of that would be a 6 there and a 1 there. Great. Does 16 go into that remainder? It does 1 time. Fantastic. Minus 16. There's 0 left. So effectively, no 8. 8 doesn't go into 0. 4 doesn't go in. 2 doesn't, and 1 doesn't. So this is the binary equivalent of 240. Now, if this looks familiar, that's a good value that we would often see in a mask, a subnet mask, if it was using those high order 4 bits. And because masks always are contiguous in the right, going from left to right, our mask values for all bits, for no bits on would be this. So no bits on an octet is going to be decimal 0. And then for 1 bit on, it'd be this 128. And then for the next bit on, I'm going to actually write this out. So I'm going to say 0 bits, 1 bit, 2 bits on in a given octet. So 2 bits on would be 128 plus 64, which would be 192. And then 3 bits on would be 128 plus 64 plus 32, which would be 224. And then 4 bits on, which would be what we just did, would be 240. And then 5 bits on would be this one plus this one plus this one. It would be 240 plus 8 more, which is 248. And then if we had 6 bits on, it'd be 248, 1, 2, 3, 4, 5, 6, plus 4 more, which would be 252. Is that right? Hold on a second. I'm going to do it longhand. So 248, that brings us to, So that brings us to right here. So 248 plus 4 more, that'd be a total of 6, would be plus 4, which in this position would be 252. And if we brought it over 1 more with 2 more bits, that'd be 7 bits in use. That would be plus 2 more, that's 254. And then if we did all bits, it'd be 1 on, plus that 1 would be 8, 255. Let me see if I got this right. 128, 192, 224, 240, 248, 252, 254, and 255. Yeah. So in a mask, guess what? We're never going to have values other than these. It has to be one of these numbers because masks don't jump around. They're not going to miss a bit here or miss a bit there. They are contiguous. So depending on how many bits are being used, they're going from left to right. There'll always be one of these values. But the way of writing it out or decoding it, as we've just discussed, it's good to know. It's good to know how to do binary to decimal. It's good to know how to do decimal to binary, regardless of what that number is. So let me go ahead and take a look at my notes again here. And let me give you a practical application of why this is, of how we could, a little bit ahead, but let's go ahead and talk about how we could use this and why it would be valuable. Let's imagine that we had 2 addresses. And one computer was using 86.75.30.9, and the other was using 86.75.40.9. So the question is, are those devices, are they on the same network or not? And the question that I want you to consistently come up with is, what's the mask? It depends on the mask, 100% here. If the mask is only 8 bits, yeah, they're both on the 86 network. If the mask is 24 bits, no, they're not on the same network because one would think it's network 86.75.30 and the other would think it's 86.75.40. So my question for you is this. If the mask was a slash, let me think here, a slash 18 for both of these IP addresses, would that mean that both of these devices are on the same network? And the question is, how many bits here in this third octet are different and where are they different? And this would be a great application of where we could just, say, let me take a look at those 2 high order bits from the IP address and see if they're the same. That's one way of doing this. So here's what we could do. We could take 30 and convert it into binary. Now, you know what I wish? I wish there was like 3 basic steps that we could follow to convert a decimal number to binary. That'd be so great. And, oh yeah, there are. 1, write out the number. 2, write out the table. 3rd, play the game called Does This Go In? And then do the math on it with just simple addition. So let's go ahead and do that. So if we did 30 in binary to figure out what that third octet is, we're focusing right here on this third octet, this third number. So we'll write out our table. It's the second rule. 1, 2, 4. And I'm going to put this up here. Here's 30. In fact, let me just let me clean this up because I want to. There we go. Write out the number. So first number is 30. Write out the table below. 1, 2, 4, 8, 16, 32, 64, 128. Great. And then we're going to go ahead and play the game called Does It Go In? Does 130 go in? Does 128 go in? No, sad. Does 64 go in? No. 32 doesn't go in. But 16? Sure enough. Happy, happy day. So we say 30 minus the 16 that went in, and we look at the remainder, which is going to be 14. So we do whatever math you want to use to get to that result. Okay, carry the borrow the 1. There's 4. Okay, it's 14. I want to show my work. Mrs. Martin, my high school math teacher in 1981, would be so proud. All right. So moving on. So the remainder is 14. Does 8 go into 14? And the answer is yes. So we put a bit there on, and the remainder is 6. So we could 0, 4, 8 was there's 6, and I'm just doing the backwards math to make sure it's right. Great. There's our remainder. Does 4 go in? Yes, it does. So minus 4. We have 2 left. That means 2 goes in. Remainder of 0, and then the 1 does not go in. So there is 30, I believe. Let me check my notes here. I'm just checking my math because this is gonna be recorded. Or it is being recorded. And I want to make sure that if I'm leaving it for posterity, I want to make sure it's right. So 0001 1110. Perfect. Okay. So there's the 8 bits for 30, and let's do the same game in a different color for 40. So for 40, we write our table. 1, 2, 4, 8, 16, 32, 64, 128. And we'll play the game, does it go in? No. No. Yes. 32 goes in. There's 8 left over. I'm going to show my work here. That means 16 doesn't go in. 8 does go in, and then the rest are going to be zeros. There's nothing left after we minus 8. So there's the binary value for 40. And so if the mask, and let's go ahead and use the 18-bit mask. If we have a mask of 18 bits, I'm going to put this in, let me put it in blue. That means if this is the second octet, the end of the second octet right here, and we're looking for 2 more bits in, so 16, 17, 18, that makes the dividing line right here. So if we look at the bit values in those 2 high order positions, guess what? These 2 IP addresses, 30 and 40, they are in the same network because their network address is identical. The 86, the 75, and the first 2 bits of that third octet are the same. If we changed it to a 19-bit mask, and I'll put this in a different color, like a dark, this one. If we had a /19 and the mask was here as the dividing line, these 3 bits from the client with .30 are different than these 3 bits from the client with .40, and as a result, they would be on different networks. And I'm going to share with you don't need to memorize that part yet. I'm going to share with you how to do very rapid subnetting and using some very cool block techniques and finger counting methods that'll make you a subnetting ninja and not have to go down to the binary very often. But you need to understand behind the scenes what's happening with it. So our goal in this video was to understand how to convert a decimal number into binary. And there's 3 rules or 3 things we need to do for it. Number 1, take out that decimal number and write it down. Second step, write out that table of the binary values from left to right. So from right to left. So of course I'm flipped. Anyway, so from left to right, write out your binary values from right to left as I point from left to right. The 1, 2, 4, 8, 16, 32, 64. And then you play the game. Starting at the 128, does this number go in wholly at least once into the decimal number? If it does, you put a 1 there. If it doesn't, you put a 0. Then you take the remainder, if there is one, the remainder of that number, and then you go to the next value. You just repeat that process. So if you've been with me for all of these sessions, here's what you now know about IPv4 addresses. This is a great, and if you haven't, if you're just joining us, go to that playlist for Subnet Saturday and take it from the top. We know that an IPv4 address is 4 numbers long. They're decimal. Those 4 numbers are separated by 3 periods, so that's why it's often called dotted decimal. And the numbers range from 0 to 255, because that's the range you can get out of 8 bits. We then took a look at how the mask does the dividing of a network, the network portion of an IP address, and the actual host. And that is when the bits stop in the mask, that's the dividing line. Everything to this side is the network, everything to that side is the host. We then identified how to convert from binary, 1s and 0s, to a decimal number, simply by adding up the bit values that are on and then summing them together, adding them together. And now in this video, we've taken a look at how to do the flip side of that, and that is to take a decimal number and do 3 basic things to convert it to binary. Write out that number, write out the binary values, and then play the game. Does this go in? Starting on the left, does 128 go into that number? Yes or no? If it's yes, yay, you put a 1 there. If it's no, we think sad, and we put a sad circle, meaning a sad 0. And that's how we build out the binary value for it. And if we want to go from binary to decimal, we simply add up those values. And we had some practice with that today as we took a look at masks. So I'm so grateful that you've joined me for this live stream. I want to make sure that these live streams are useful. If you like the video or got some value out of it, or if you already know subnetting, you're just here for a good time, let me know. Either a thumbs up. Also the comments. Here's what I discovered something new. And that is, if I trim the beginning of a live stream, which I usually do, all the live comments no longer visible. So if you have a question or a comment or something else, this video will be live in about 2 or 3 hours on the site. If you want to come back, just leave a comment or a question. I'd be happy to take a close look at it then. Also, if you haven't done so already, please feel free to subscribe. If you like the video, if it was useful or entertaining, go ahead and click on the like button. And that's it. So my goal for this channel and these separate sessions we're doing is to make content that's useful, really useful for learning the CCNA, the Cisco Certified Network Associate, which is the exam 200-301. So if that's what you're looking for, this channel is for you. I hope it's useful. And I'll see you in the next live stream, which from this perspective is tomorrow, which is CCNA Sunday. So until then, have a great day. Enjoy the rest of your weekend. And we'll see you soon in another live stream. Thanks, everybody.